So what they basically did in this paper was to take the one they already proposed, that is the multiscale vision transformer, and make a couple improvements to reduce the computational power needed and to improve the performance. So as we all know, historically, there have been architectures, mainly CNNs, that take all the recognition tasks, object detection, classification, segmentation, and that have simplicity and efficacy. Nowadays, the vision transformers have had a promising performance revolving these methods, but they have a big challenge, that is that they need high resolution information considering the task that they have to solve. And this high resolution scales the computation and memory complexity quadratically due to the structure of the transformers. So as we know, we use tensors for query, for values, and for keys, and this is what gets this complexity quadratic. So there have been two common used strategies. One of them was proposed by them to solve this computational challenge. The first one was proposed by Swin, in which basically they take some windows and they take a local attention over it, as we can see in the left image. And in the right, what they proposed in the previous paper was the pooling attention, which means that the tensors of query, values, and keys were smaller, so they could reduce the computational needs. What they did in reducing the query, they achieved a reduced resolution dimension between the stages and also in the output dimension. When they shortened the keys and values tensors, they could reduce the memory and the computation complexity. So this is the approach they made to avoid this challenge. So in context, the transformer they proposed, the multiscale vision transformer, basically extends the already existent vision transformers in a simple way that all of us already have a sense of knowledge. That is sort of what CNNs did, and is reduce the size of the image through the scales, through the stages, while incrementing the features. So this paper, they propose some of the improvements, but specifically what they wanted was to generalize not only for image classification, but also to apply it to object detection and video classification. So as we can see in the image, they use their transformer for image classification and video recognition, but for object detection, they have to use it to extract the features, but they use a feature pyramid network to generate the object detection. So in this study, they seek to encompass a couple of things that I'll be explaining through the presentation. So in the pooling attention, they took two main things. The first is use positional embeddings, shift invariant ones, to inject more information or positional information into the transformer. And second, the residual pooling connection, they made a lot of experiments using all the possible residual poolings to compensate the effect of these strides that they make to shorten these tensors. What they encountered was they are only using a residual pooling connection, and not on 3 of them, but this is completely on experimental empirical studies. So as I already mentioned, they also use the transformer, but with a feature pyramid network to generate object detections and instance segmentations. So they make a little twitch to it in the sense that they are using hybrid window attention. That is something they propose in this paper to differentiate themselves from other proposals like the shifted windows that the swing transformer already proposes. They encountered that these changes, or this hybrid window attention proposed, complements the pooling attention that they already had and get a better performance. The architecture they proposed it in different sizes, 5 specifically, so that they can compare it to different methods. As we will see in other slides, they use specific sizes for specific comparisons. So in the related work, we'll know there are CNNs, but they focus on vision transformers. And in this case, the vision transformers only were applied to image classification, and what they did in multiscale vision transformers was do the same, but in a different manner and a more specific proposals. Now, what they are seeking is to, or what they did, is to generalize to other tasks like object detection and segmentation. As I mentioned already, the window attention is something they did experiment on to see if the hybrid window attention that they propose is better or can compensate other proposals. Finally, in MViT recognition, they made experiments with pre-training on large databases like ImageNet, because in previous works, some of the methods achieved better performance doing so. So they compared their method pre-training also on ImageNet. So revisiting this multiscale vision transformer, I already mentioned what they did by pooling the tensors, and they use the multiscale, sort of what we did in CNNs, to analyze their features in a more efficient way. So I'm going to talk about 4 main things: the improved pooling attention they proposed, the applications for object detection, video recognition, and some different architecture variants. So in the improved pooling attention, what they first proposed is a decomposed relative positional embedding that, as I already mentioned, is to include in the transformer the positional embedding. It is decomposed, you will see, because the computational power required is much smaller. So this study incorporates relative positional embeddings so that the understanding of the context is much higher. And in the video recognition, this helps also with the temporal spatial context. So as we can see in the bottom formulas, what they are doing, different from the attention that we already know from transformers, is adding this E, that is once more the queries, but including this multiplied by these new positional encodings. What they saw is that in doing so, they had a scale in the positional embeddings that in possible embeddings, there are time times width times height possibilities. So this increases the complexity of the model. So they propose what is in the bottom, that is doing it decomposed along the height, width, and time position. And in this sense, the scale of these learnable embeddings is no longer a multiplication, but an addition of the components. So afterwards, in the residual pooling connection, they, as I already mentioned, they experiment doing residual pooling connections. This is not in the main paper, but they do mention they experiment in 3 of the tensors, so the query, the key, and the values. But after doing all the ablations, they saw that only doing so in the Q tensor will increase the information flow and facilitate the training of pooling attention blocks. So we can see that initially they had the attention as we already know it, and now they are doing the pooling connection, the residual pooling connection, and in the case they are using the pooling in the query tensor, this residual connection will include the pooled one. We can see here that they would have the same size. So there's no mistake adding these two. Here I show the original architecture they had and the modifications they made. So we have here the residual connection of the queries, and here we have the decomposed positional embeddings. They did not mention these additional changes in the main paper, but they did in the further work. So they do a couple more things, like that the channel dimension expansion is done not in the last MLP block of prior stages, but in the first transformer block. This is a subtle change, but this reduces the parameters and flops without having a big change in the performance. Also, they removed the class token so that they had a much smaller training time. And what they did instead was that the output tokens were averaged, and then the final classification head was applied. So this is not much important, but are some of the changes they made to reduce the computational power when maintaining a high performance. Okay, so in the object detection and instance segmentation tasks, as I already mentioned, they use the feature pyramid networks because they already have these reduced resolutions. So what they had to do was include this information of each one of the layers in the FPN to have predictions. The FPN could be any FPN-like network, like Mascar CNN, for example. That was the one they used, and they also compared to similar ones like a Cascade Mascar CNN. So furthermore, they proposed the hybrid window attention in comparison to a normal base window attention and the one proposed by the swing transformer. So this paper approaches how to reduce this compute and memory complexity significantly. So they have the already mentioned pooling attention, and the window attention they used as a technique to reduce computation for object detection. Here I show that the approaches are the same. Both approaches are the same in what they seek to achieve, but they have some subtle differences in the intrinsic natures. So the pooling attention, what does is segregate or shorten the tensors via local aggregation, but the window attention does a specific attention over a smaller window. So the resultant tensors will be also smaller. The swing approximation, as it can be seen here, is that in one layer, the windows are in one way, and then they shifted for a second layer so that they have like overlapping windows between layers. What they propose here is doing just a simple modification to the original windows so that they do not have these cross-window connections kind of in the swing, but they do have modifications in the original window embedding. Okay, so in this transformer, the positional embeddings are first initialized in the ImageNet pre-training weights corresponding to 24 times 224, and then they interpolate to the respective sizes for object detection. So we know that in ImageNet we seek to classify, so the size does not have to be changed. In this case, they are seeking for object detection, but to initialize a pre-trained, for instance, model, they use the original one and then interpolate it to the size of the object detection they are seeking for. In the video recognition, as I already mentioned, there are not much changes. There are only changes in how we have to understand the changes. So first, the projection layer in the patchification is now not only a 2D patch, but it becomes a 3D space-time cube where we have all the frames. And the second, the pooling operators now pull spatio-temporal feature maps, as I already mentioned. And third, the relative positional embeddings reference the space-time locations. When I mentioned the width, the height, and the time, now in this application, we will have that time component. So note that for the first and the second, when we initiate a pre-trained model, we would have only 2D information. So what they did is that the weights they used were in the center frame, and for the rest of the frames, they initialized them in zeros. The same with the third, they initialize all the temporal embeddings in zeros, and they use the information of the ImageNet pre-training for the width and the height. So some variants they proposed were 5 in total. They do this not only to compare themselves to other methods, but to use them in different scenarios. So the difference is just the computational power, in other words, as we can see in the flops and in the parameters, and they do so by having larger amount of base channel dimensions, number of blocks in each stage, and number of heads in the blocks. So for the results, as Paulo mentioned, mainly what we are going to see is that they outperform every method they include in the comparison. So they include a lot of other architectures. Here too, it is important to see they compare themselves to their previous work, but not necessarily in the same sizes, but they demonstrate that they outperform by far other methods, including CNNs. What's important here, for example, in red, is that they do modify or increment their input image. So in this comparison, they are not comparing to the same input image size in the previous iteration, but they do outperform. In the image classification, pre-training on ImageNet 21K, they increased by at least 2 points the accuracy. So they demonstrated that what previous works did was in fact something they could use. As we can see here, they achieved almost 89, and previously they have around 86 points. So in object detections, in COCO, for instance, they use the two architectures, the mask RCNN and the cascade RCNN, and they experimented on both with all the modifications, with the pooling, the H-win, and the swing transformer that has its own window attention. So the backbones are pre-trained or on ImageNet and then fine-tuned on COCO. What I mentioned, and here we can see that effectively they outperform all previous methods. It is important to note that, for example, here they are using different methods they propose of training, for example, the pre-training on 21K, and they keep on getting better in performance. What they are mostly proud of is that in most of the cases, they outperform methods while reducing the flops and the parameters. For instance, we can see that in this small, we have 54 parameters and a better performance than some of the CNNs and some of the transformers that have a lot more of parameters. In their experimentation of different self-attention mechanisms, they saw a different behavior between both of the approaches. Here we have the original vision transformer and the multiscale vision transformer. They concluded here that that only doing the pooling gets a better performance, but they changed their writing or their conclusions to a straight 8, because they say it's important not only to have a good performance, but a good trade-off between memory, flops, and accuracy. So in the previous one, they are proud to show that when they have the full attention mechanism, they achieve 82, but when doing a fixed window, it is reduced. The same with the swing mechanism, but using their now proposed H-win, they not only recovers it, but gets a better performance by a small margin. Here in the mask RCNN on the COCO detection, they show the same that I was mentioning, that although the pooling and H-win is not the better performance, they have a better trade-off. So they focus a lot on some cases on the trade-off when it's something they propose, but when they do better than other methods, they do not mention at all the trade-off. So for instance, here, they do not outperform the normal pooling, but they mention that this is the best method because it has a better trade-off. So they did a lot of ablations. For instance, they did a positional embedding ablations, and they compared their decomposed relative position. And to the conclusion they get is that the accuracy and the APbox on COCO is better, and if it is not better, it has some some benefits like the training iterations per second over other methods. Here we can see that actually that's not completely true, because they have a better performance with no positional embeddings or absolute positional embeddings. In terms of performance, they have with joint relative position, positional embeddings, and the decomposed one. So for the residual pooling connections, as I already mentioned, I did not include that table, but they did experiments in all the three tensors and decided that the only one that affected and that gave them the smaller computational needs was doing the residual pooling in the query tensor. Here we can see that the accuracy is actually improved using both only residual or the residual pooling plus the full Q pooling, and that they outperforms by not that much, but they do have a computational power that they need, extra computational power, because it requires more memory than before. So in runtime comparison and in single scale versus multiscale for detection, once more, they show they are the state of the art nowadays, but they do talk a lot about the trade-offs. So in some cases, they show that they have the same, for instance, a test image per second that swim, but that they do have different amounts in ImageNet, for example. So they compare a lot of methods, they compare a lot of databases, and basically conclude that in most of the cases, they are the best in computational recurses, and that in performance, they are the state of the art. So in video recognition, there's not much to discuss. They, once again, establish themselves as the state of the art, but there are some things we can see in these results. Now they are using the pre-training they didn't use in their last iteration, and they make some twitches that they did not make. For example, for instance, to achieve the state of the art, the new state of the art, they used a different input image size in the large version of this version, which is now not 312 but 352. The other values, the 40 times 3 is the number of frames and the number of you can say pooling between these frames they are using. They also evaluated on other databases. Here I include something V2, but they did over a lot more databases. Once more, they were the state of the art, but once more they assured themselves that using the pre-training on ImageNet or even on Kinetics did improve their performance. Plus, they have some of the new improvements, so they achieve a lot higher metrics. Here they did some ablations so that they could assure the effect of these pre-training datasets, as I already mentioned. And they showed that training from scratch does have lower performances than pre-training on ImageNet 1K or 21K. So they conclude that this is the improved version of their transformer, and that they seek to have a hierarchical architecture for visual recognition, but in a generalized way. So they wanted to generalize it to object detection, instant segmentation, and video recognition. And they showed that they were the state of the art with this method. Lastly, they mentioned that first, to reduce the full hyperparameters, they used all the recipes, they call it like that the state-of-the-art methods are using nowadays in order also to compare to them. So they did not experiment on the different variations of their parameters. So they mentioned that the choice of these hyperparameters may not be or may be suboptimal and could have some improvements in a next iteration when experimenting on them. Also, they mentioned that although they have the 5 different sizes of these transformers, they did so to compare themselves to other methods, but that they are seeking to do some smaller ones so that this could be a tiny ML application or to mobile phones or different applications, and also to bigger amounts of large-scale data scenarios. They would like to make some even larger models. And that's most of it. Here I have a note, and is, for example, there's the first transformer proposed for object detection, the detection transformer. They do not mention it, but it's more than clear they leave it behind. The detection transformer, or the deformable detection transformer, achieves metrics on COCO, for instance, of less than 50 points. And as we saw, they outperform this metric. And what is funny enough is that for object, when they presented the first version of this transformer, they presented it as a solution for not using CNNs, because, for example, detection transformer use a CNN to extract features, but in this iteration, they do include the feature pyramid networks, but they do it in the inverted way. So they use the transformers to extract the features, and they pass it to the network to do to apply the object detection. And that's all of the presentation. Thank you very much.